Hello children, today I'll be discussing with you the exercise questions of the human eye and the colorful world. So let us start. The human eye can focus on objects at different distances by adjusting the focal length of the eye lens. This is due to, the answer for this question is accommodation. Children, human eye can change the focal length of the eye lens to see the objects situated at different distances from the eye, and this fundamental is called power of accommodation of the eye. Okay, now the second question. The human eye forms the image of an object at, remember, the image of the object is always formed at the retina of the eye. Okay, now question number 3. The least distance of distinct vision for a young adult with normal vision is, the answer is C, 25 centimeter. The least distance of distinct vision is the minimum distance of an object to see clear and distinct image. Okay, so if a normal eye wants to see a clear distinct image of an object, the minimum distance at which it can do so is 25 centimeter for young adult with a normal vision. Alright, now number 4. The change in focal length of an eye lens is caused by the action of ciliary muscles. Remember, ciliary muscles are responsible for the change in the focal length of the eye lens. How? They contract or relax, changing the curvature of the eye lens, and therefore in this way, by changing the curvature of the eye lens, they change the focal length of the eye lens. Okay. Question number 5. A person needs a power of minus 5.5 diopters for correcting his distant vision, and for correcting near vision he needs a lens of plus 1.5 diopter. You have to calculate the focal length in each case, focal length of a lens which will be correcting the vision problem. Okay, so for that we have to use our formula. So सबसे पहले we will start with number 1, that is the distant vision. For distant vision, what do we have? We have the power given to us as power is equals to minus 5.5 diopter. Okay, so in order to calculate the focal length, we will use the formula 1 by power. If the power is in diopters, the focal length which we will get will be in meters, remember. Okay, so we will place the value 1 by minus 5.5. Okay, when we place this value, what do we get? What do we get? We get 0.181 meter. Alright, so this is the answer for distant vision. Okay, 0.181 meter. You can convert it into centimeter also, 18.1 centimeter. Same way, number 2, for near vision. For near vision, the power is given as plus, the sign will be negative, don't forget to give the negative sign, plus 1.5 diopter. So again we will calculate the focal length, that will be 1 divided by 1.5. Okay, did I make any mistake, children? No, na? So this will be how much? 0.667 meter. Alright, so your correct answer for distant vision, it will be 0.181 meter minus 0.181 meter, and for the near vision it will be plus 0.667 meter. Alright, so this is the correct answer. Now let us come to question number 6. The question number 6 says, the far point of myopic person is 80 centimeter in front of the eye. Okay, what is the nature and power of the lens required to correct the problem? Okay, in order to do that, we'll just erase the previous question. Yes, and then we can do it. We can utilize this space to solve the next question. Sorry. Yes. So my next question will be, first I'll write down the data which is given to us. It's a, you know that the person is having a myopic eye. That means the person is suffering from myopia. A person who suffers from myopia, image is formed in front of the retina and not on the retina. Remember that. So here the object distance u is infinity. Alright. The image distance v is in front of the retina, it is forming, so it will be minus 80 centimeter. If it would have formed behind the retina, then plus 80 centimeter. Okay, so since it is in front of the retina, so minus 80 centimeter. And we need to find the focal length. What are we going to use? The lens maker formula. 1 by v minus 1 by u is equals to 1 by f. Let us place our values. 1 by v is minus 80 minus 1 by infinity is equals to 1 by f. Alright, so 1 by f will be minus 1 by 80. Alright, so if you solve this, f is minus 80 centimeter, which you can also write as minus 0.8 meters. Alright, so you got your focal length. From here you will get your power. How? 1 by f in meters. So 1 by 0.8 negative of that. Okay, so the answer which you will get will be, the power will be equal to minus 1.25 diopter. Alright, so this is the answer for the power of the corrective lens which we are going to use. And since it's of negative, that means that the lens is a concave lens. Which lens are we going to use? A concave lens. Clear, everyone? So question number 6 done. Now let us come to question number 7. Let me erase this off before we enter into another question. I hope you all have understood this. Next time I'll open one more editor so that we can do the solution at another page and question at one page. Okay. Number 7. Number 7 says make a diagram to show hypermetropia. Oh, we need a big space for this. So maybe I'll do this at the end. Okay. Let me go to number 8. Why is a normal eye not able to see clearly the objects placed closer than 25 centimeter? Children, I just now discussed with you that islands over here, the least distant of distinct vision is 25 centimeter. Okay. And the curvature of our islands can be modified to some extent only by the ciliary muscles. However, the ciliary muscles have certain limits. Okay, so that is why the focal length of the islands cannot be decreased below that certain limit, and that minimum limit is 25 centimeter. So a normal eye will not be able to see clearly the objects closer than 25 centimeter. The eyes will be put to a lot of strain if they want to see objects which is closer than 25 centimeter. Alright, 8 done. Number 9. What happens to the image distance in the eye when we increase the distance of the object from the eye? Okay, if you increase the distance of the object from the eye, nothing will be affected. The image distance will remain constant and image will be formed on the retina itself. Okay, what will happen is since the size of the eyes cannot increase or decrease, the image distance remains same. When we increase the distance of an object from the eye, the image distance in the eye does not change. It still forms on the retina. The increase in the object distance is compensated by the change in the focal length of the eyelens. That means the ciliary muscle starts adjusting the focal length of the eyelens if the object distances changes. Okay, so the lens may become thinner. Alright, so this is what it is. Number 10. Why do stars twinkle? Now children, why do stars twinkle? The phenomena, the reason behind the twinkling stars is atmospheric refraction. Atmospheric refraction. Okay, layer by layer, from denser to rarer or from rarer to denser, refraction takes place. Okay, in this case, from denser to rarer or rarer to denser, whatever you can say, the refraction takes place, atmospheric refraction, depending on the layers of the temperature. Okay, and because of this atmospheric refraction, we see stars twinkling. Okay, stars are usually point source of light. So when light comes from the stars, it enters the Earth's atmosphere. It gets refracted at different levels because of the variation in air density and temperature. When the starlight refracted by the atmosphere more towards us, it appears brighter. And when it comes less towards us, brighter than it when it comes less towards us. Therefore, it appears as if the stars are twinkling. Okay. Now question number 11. Explain why the planets do not twinkle. Children, planets are extended objects, not like stars. Okay. So they do not twinkle because they appear larger in size than the stars. They are relatively closer to the earth. They are considered as a collection of large number of point sources of light, whereas planet is a single point source of light. So the different parts of these planets produced either brighter or dimmer effect in such a way that average of the brighter and dimmer effect is zero, and therefore they don't appear twinkling. Okay. Now number 12. Why does the sky appear dark instead of blue to an astronaut? Okay, the sky appears dark instead of blue to an astronaut because there is no atmosphere in the outer space. Remember that can scatter the sunlight. Okay, so why do we see the sky light? Because of the scattering of the light, right? Why there is orange light during sunset or sunrise? Because of scattering. So when there is no atmosphere in the outer space, there is no scattering of light, and hence what you see is nothing, no light. Okay, so they appear dark to the astronauts. Alright, now coming back to question number 7. For that, I need to show you a diagram, or you can just refer your book. It's given in your book, the diagram, in a way that hypermetropia is corrected. If still you don't find the diagram in the book, then please mention in the comment section. I'll make a short video for you to get help from there. Okay, thank you, children.